we're going to look at the simplest type of motion, periodic or oscillatory motion, called simple harmonic motion, or SHM, simple harmonic motion. So I'll use this abbreviation throughout the course of these series of lectures, but know that if I use SHM, and I'll probably say it out, I mean simple harmonic motion. So simplest of oscillatory systems. So we have a wall again. Attached to that wall is a stiff spring. And attached to the end of the spring is some mass m. So this could be massive, it could be very, have a lot of inertia or a very small amount of inertia. And the spring could be a very stiff spring, or it could be not a terribly stiff spring. But those are the two variables. There's no friction as the mass moves on the table. I'm not worried about frictional forces here. When the spring is not compressed or extended, the mass is at its equilibrium position. We define that to be x equals 0. Then if I stretch out the spring to some distance before I let it go, I've stretched out and I move this mass here. The spring is stretched out. It's still attached to the wall, but it's stretched out. Now I'm at some position capital X, and I have a big X drawn with little serifs on the top to represent that's a capital X. This is the maximum displacement of the mass from the equilibrium position. We call that the amplitude. Now, if I were to let this go, what would happen is there would be a force pulling this mass back towards the center. As this mass passed the center, all of the elastic potential energy stored in the spring would be translated into kinetic energy. But the spring wouldn't stop at the equilibrium position. It has all this kinetic energy now. And there's no elastic potential energy at the equilibrium position. So the mass compresses the spring. As it compresses the spring, kinetic energy goes into elastic potential energy. The spring gets compressed, all that energy is stored in the spring. And then the mass stops moving to the left and then moves back to the right. So what happens is you get oscillatory motion, back and forth, back and forth, back and forth, around the equilibrium position. Now, note that the amplitude, capital X here, is the biggest deviation from the equilibrium position. You cannot get further from the equilibrium position than X. Right? Some of you have probably pushed children on swings or pushed friends on swings when you were younger, right? You pull a child back on a swing, you let them go, they go forward, when they come back, they don't hit you in the face. Assuming they're not pumping, assuming they're just swinging back and forth. So that maximum amplitude stays the maximum amplitude. Now, if there's no friction, there's no wind resistance, that child will swing forever. But that's not how the world works. This motion, back and forth, back and forth, back and forth, is periodic. So what is the period? How long does it take it to complete one oscillation? Well, there are two factors we have to worry about, potentially three, right? It depends on how stiff the spring is. If the spring is really flimsy and weak, it's not going to provide much force to the system, so the system will be slower. If the mass is very, very large, it has a lot of inertia, it's harder to move and it's harder to slow down, so you would imagine it would be slower. And the amplitude, right? Maybe it depends on the amplitude too, because the bigger the amplitude, maybe the longer it takes to go through one oscillation, because that's to travel further. Well, it turns out that last one doesn't matter, and we'll talk about that in a moment. The equation to figuring out the period, T, of a simple harmonic oscillator is given by this relationship. It depends on this factor 2 pi, that's just a constant. Pi is 3.14 that you're all familiar with from geometry, times the square root of the mass of the block at the end of the spring divided by k, lowercase k, that spring constant, that elastic constant. So again, the bigger the m, the bigger the period, the harder it is to move that mass and harder it is to slow it down. And inversely proportional to the square root of 1 over k, where k is the stiffness in the spring. So if the spring is not very stiff, then it has a smaller period. If the spring is very stiff, then the period, or it has a bigger period. If the spring is not very stiff, it has a smaller period. Now, period and frequency were inversely related. We learned that in the last video. So if I solve this, 1 over the period is 1 over this, solve it for the frequency, I get this equation, right? Everything's flipped. Instead of 2 pi, you have 1 over 2 pi. Instead of the square root of m over k, you have the square root of k over m. So you can easily calculate the frequency of a simple harmonic oscillator here, or the period of a simple harmonic oscillator. It depends on the mass, and the spring constant does not depend on the amplitude. This equation, nowhere in this equation does it depend on the amplitude. And that's a little counterintuitive and can be difficult for some people to grasp, but it's easy to test. Go to a local park with a small child, preferably one you own. Take that child in the swing and pull them back a small distance, let them go, and time how long it takes them to go through 10 swings. And then divide that by 10, and that's the period. Then take them and bring them back a medium distance and let them go. And count how long it takes them to complete 10 swings. Then put them in a very large distance and let them go. Again, don't have them pump, just have them swing back and forth neutrally. You'll find that the period is almost identical. I mean, the only difference will be in your timing. The period does not depend upon how far away you are. And the reason for that is because the further your displacement, the greater the force. The greater the force, the greater the acceleration. If you pull that child back further, they accelerate faster, but because they have a greater distance to go through, those two things end up canceling one another, and it's the same period. And we'll do an experiment on this semester, which will show this. In fact, we probably might have already done the experiment, given the timing of our labs. But the period and the frequency of a simple harmonic motion does not depend on the amplitude. Well, let's look at this. Let's actually graph with time what the displacement is of this simple harmonic oscillator from the equilibrium position. Here we have a plot showing the displacement x as a function of time t for that simple harmonic oscillator. Now it starts off at some maximum displacement, the amplitude, positive x. So I've stretched out that spring in the previous example to its maximum amplitude and then let it go. And when I let it go, I start the timer. So time t of 0 is that maximum amplitude. Then it passes back through the equilibrium position 0, compresses the spring, and is at its smallest negative amplitude, when the spring is most compressed. And then it goes back through the equilibrium position and it ends up being stretched, back through the equilibrium position, compressed, and so on, repeating this motion as a function of time. So this is its displacement in the x direction as a function of time. So you can see it's periodic, right? It's a sine wave or a cosine wave, if you remember back to geometry. So it's an oscillation, simple harmonic motion. Now, I can, if I know some of the information, like the period here, the time between the time for one full oscillation. So either the peak to peak difference here is the period, or the trough to trough distance in this graph is the period. If I know the period, and I know what the amplitude is, x, I should be able to come up with an equation that tells me what the actual displacement x is as a function of time, because x is clearly changing as time is changing. Well, there's a very simple relationship, or relatively simple relationship, that gives the position at any time t. I need to know what is the maximum amplitude. I need to know cosine term here, that's just a function, 2 pi, which is a constant. T is the time I'm interested in. What is the time? Where is the simple harmonic oscillator at 1 second, 1.5 seconds, 2 seconds, 8.3 seconds, whatever time I'm interested in, divided by t, which is the period. Now, this can confuse some people. X with t embraces, sometimes it looks like x times t. That's not what this means. It means x is a function of t. So sometimes you might see it written as like this. Other times, and I prefer, if it's written, oops, we'll use the blue to be consistent, x as a function of time. and then put time in sort of a little, as a subscript. So I want the position at some time t. That's given by this blue equation here, the top equation. So if I plug in time, if I know what the period, let's say this oscillator, the maximum displacement is 1 centimeter, the period is 1 second, I can go then and plug it in for what is its position at half a second, 5 seconds, 3.8 seconds. Whatever time I want, I can calculate what the position is. But the simple harmonic oscillator isn't just changing position, it's also continuously changing speed, right, or velocity. Its maximum velocity is at the equilibrium position, and its minimum velocity, or 0, is at either end. So I can actually use these equations. Now it requires some calculus and a derivation, which we're not going to show, but the end result is still an algebraic equation. So the velocity at any time t is equal to the maximum velocity, negative of that maximum velocity, times the sine of 2 pi t over the period. What is the maximum velocity? Well, it's given over here. The maximum velocity that the simple harmonic oscillator can get is 2 pi times the amplitude over the period. So I know what the amplitude is, and I know what the period is, and I need to know those things to get position. I can also find out velocity. Finally, again, taking another derivative, if you have calculus. If not, then we'll just show you the algebraic equation. The acceleration. Because this simple harmonic oscillator, its velocity is constantly changing, which means it's constantly being accelerated. And unlike before, it's not a constant acceleration problem. It's not like gravity or free fall or the constant acceleration equations we used way back in the early chapters earlier this semester. This acceleration changes with time. Acceleration as a function of time is equal to minus the spring constant k over the mass m of this simple harmonic oscillator times the amplitude, capital X, times the cosine of 2 pi t over the period. So this cosine term is the same as the cosine term up here. You just have negative k over m added to the beginning of that equation. And remember that the acceleration, force is mass times acceleration. So if I know what the acceleration is at any time t, I can multiply that by the mass at the end of the spring. I can tell you the force at any time t, because the force is continuously changing as the spring is getting stretched and compressed. So these are time-dependent kinematics equations that are strictly for simple harmonic motion, simple harmonic oscillators. So you cannot use these on free fall motion or anything like that because that's not periodic. But once you have the amplitude, the period, you can figure out what the position is at any time, the velocity is at any time, the acceleration it is at any time, and if you know the mass, you can figure out what the force is at any time. You also need the spring constant and the mass to figure out the acceleration. So a lot of information you can get from these simple harmonic oscillators.